Okay, everyone. I want to make a video for today's lesson. So today is day 8, and we're going to continue with the linear programming. We got one more example to talk about here. A couple of other things, though. We do have the exam starting next week. We'll be spending some time this week for review, and then your project is due this week as well. Your Google Slides should be uploaded to Moodle by Thursday night, along with your individual write-ups. And then on Friday, we'll have each group kind of quickly present their little slides and their problem. So let's go ahead. So this is one of the activity problems from Friday. Here's just the quick answer. If you need to pause the video to take a look at this, there is the answer to it. We see that the combination of 2 and 2 gives us the minimum, or this is a minimizing problem. Minimize the cost, of course, that's what we want to do. So we're minimizing the cost. So that combination of 2 and 2 does that for us. This would be the answer to the question, because we're looking for what combination and how much would that be. The second one was a maximizing problem, and we're trying to find out what combination would give the most. And it turns out 0 and 3,000 would. So again, the revenue in this case, we want to maximize that at 150,000, and we can do that when X is 0 and Y is 3,000. So that's just a little review of those. Okay. Today's handout, today's notes, we're going to talk about a linear programming problem that might have more constraints to it than what we've been doing so far. In this example, and I'll let you can pause the video and take some time reading through it. But basically what we're doing is we have a coffee supplier has 2 warehouses in Minneapolis and Denver, and they need to ship out some coffee to both of their retailers in Seattle and Chicago. And in here are the details of how all that lays out. Okay, and our goal is to find the number of pounds to be shipped from each warehouse to the retailer and minimize the cost, of course. Okay, so how do we do that? Well, I always like to start with a diagram. And so on your handout there, you'll see that there's a diagram that kind of looks like this. And we think, okay, what's going on in this problem? Well, they're shipping from Minneapolis and they're shipping from Denver, and their choices are going to Seattle or to Chicago. All right. And according to all the numbers in there, all the things in there, so we've got how many pounds really is kind of the question we're going for. We want to go find the number of pounds to be shipped from each warehouse, right? So that number of pounds to be shipped from each warehouse, that would be our variables. Those are the things we get to choose. Okay, so we can say the number of pounds from Minneapolis to Seattle could be X. The number of pounds from Minneapolis to Chicago could be Y, right? So we don't know exactly how much that's going to be. And then from that, we can go, okay, well, how many pounds would they ship from Denver? Well, if they're shipping X from Minneapolis, then they would do 400 minus that X because Seattle needs 400 pounds, right? Seattle needs 400 pounds total. So whatever we send from Minneapolis, Denver will send that subtracted from 400. And likewise to Chicago, what is Denver going to send to Chicago? Will be 350 minus however much Y is. Okay, so that's our goal, is to figure out what is that Y and X that would minimize the cost. And then let's see what we have about cost here. Okay, the cost of shipping from Minneapolis to Seattle and all that. Okay, so the cost of shipping from Minneapolis to Seattle is $2.50 per pound. The cost of shipping from Denver to Seattle is $2 a pound. And then from Minneapolis to Chicago will be $3.50 a pound. And from Denver to Chicago is $2.50 a pound. Okay, so those are the shipping costs. Those are the constraints, right? And like we said, that the X and Y represent the pounds of coffee shipped from Minneapolis to Seattle. X represents that, and then Y represents the pounds of coffee shipped from Minneapolis to Chicago. The pounds, the number of pounds of coffee. So whatever X and Y are equal to, those are the number of pounds. All right. So now we need to set up our system of linear equations. Okay. And we have our setup here. So we want to figure out, okay, what are our constraints on this? Okay. We can't be negative, obviously. Let's go ahead and look at these inequalities. It's based on what we see in the problem. Okay, I'm just going to kind of go through this a little bit. We know that X plus Y has to be less than 700 because back in the problem, Minneapolis only has 700 pounds to pull from. Okay, so whatever Minneapolis sends has to be less than 700. Okay, so which means then that what Denver sends, because Denver has less than 500, is going to be this 400 minus X plus 350 minus Y. And we can, of course, simplify that down a little bit so that we see that X plus Y must be more than 250. Okay, do a little simplification there. So that Denver, whatever Denver sends, has to be more than 250. Okay, so we've got those two inequalities right there that show our constraints on the number of pounds. Minneapolis can't send more than 700. Denver can't send, has to send at least 250 for this to all work out. And let's see, what does Denver does Denver say how much, what's their maximum? Denver has a maximum of 500. Okay, so they can't send more than 500. So that would be another constraint on the system. Okay, right, so there we go. They're going to be at most, okay, so and this is the other constraints that Minneapolis to Seattle doesn't want more than 400, so X must be less than 400, and 350 would be the maximum on Y because Chicago doesn't want more than 350. Also, X must be positive and Y must be positive because we can't have negative values. So we're actually finding boundaries here both on X, not just a lower boundary like we've been doing, but also an upper boundary. So that means X can't just be anything. Y can't just be anything. They've got to be within that. So let's kind of put all this together. Let's this one first. Let's do our objective function. I guess that's the next question here. So is our cost. Okay, so what is our cost? So let's start out with, okay, we know that to ship coffee X from Minneapolis, it's going to be $2.50 times X, $2.50 per pound. And to ship coffee X from Denver, it's going to be 2 times what Denver can send, 400 minus X. Okay, and likewise, shipping to Chicago, $3.50 per pound from Minneapolis, plus $2.50 per pound from Denver. Okay, so it kind of lays out like that. Let's go through the motions and simplify it. We can kind of simplify it down, and we get our cost function must look something like this, right? 0.5x plus 1y plus 1675. Okay, and so that is our cost function that we'd want to minimize, of course, our costs. We want to minimize costs. Okay, so just restate it right there. Move down a little bit here. Okay, so that's our cost function. Okay, now let's put it all together and look at our graph. Okay, here we came up with X plus Y must be less than or equal to 700. X plus Y must be greater than or equal to 250. Those are the constraints on the 2 different pounds of coffee, or 2 different shipments of coffee. Also, we found that these boundaries around X isn't just positive. It has to be less than 400, can't be more than 400. And the same thing with Y, can't be more than 350 because the retailers don't want more than that. And then our cost function. And then if you graph it, you might get something like this. I pulled it up in Desmos here. Let's take a look at what Desmos looks like. I graphed it over there. And so we have it kind of looking like this. I did a little fancy stuff with Desmos here, but if you were to graph it, you'd have to kind of do a little bit more fancy stuff. But it basically kind of looks like this. This purple region here is our feasible region. This is the region we're looking at. We want to minimize those costs within that region. Okay, that'll be linked to the slides. I'll share these slides with you as well. So there is the graph, and there's our feasible region. Okay, now remember that we want to look at the corners of our feasible region. So in this case, we don't just have 4, we've got six different sets of pairs, 6 different pairs of numbers, 6 different combinations of things here that we can work on. So let's just go ahead and we're going to just do our objective function, right? Our objective function is that C equals 0.5x plus y plus 1675. That came from before. Okay, and we're going to try the first point, 0 to 50. Okay, we'll put that in, and we get 1925, so 1,925. That would be the cost of shipping 0 to I'm losing track of the numbers here. 0 to Seattle, and then shipping 250 to Chicago. Yep, there we go. Okay. Then we'll just repeat that for each one of these. 0, 350, 350, 350, 400, 300, 400, 0, and 250, 0. That comes from our boundaries, right? Y and X create this little, we can't keep going forever, right? So if we go plug those in, what do we get? Do we get 2025, 2200, 2175, 1875, and 1800. Okay, so those are, we use that objective function, the goal, and we want to look at which one gives us the minimizes it. Okay, since it's a cost, we want it to be as cheap as possible. Okay, and then we state, okay, what is it? What combination will work? So if we do that, which one obviously gives us the least? So the minimum cost occurs when X is 250, okay, and Y is 0, which gives us $1,800. The minimum cost occurs, so that means 250 pounds of coffee should be shipped from Minneapolis to Seattle, 0 from Minneapolis to Chicago, okay, which means then 150 from Denver to Seattle and 350 from Denver to Chicago. Okay, again, because we're using those, where'd that break down to? Right here, because we've got that 400 minus X. So if we know X is 250, 400 minus X. So we've got this pair right here. This is for what Minneapolis has, and this inequality here says what Denver has. And we put that all together, that gives us this conclusion down here. Okay, and it gives us a minimum cost of $1,800. So that is the example for today. Hopefully it wasn't too fast. You can go back and pause the video if you need to. And we'll be spending a little bit more time. If you have questions, please message me, okay? And then homework, of course, that linear programming project, work on that with your partners, partner or partners. Figure out who's going to work on the slides, who's writing all the slides. That's due by Thursday night again. Okay, your individual write-ups are due also. There's a place in Moodle to upload that. You can click on the link right in Moodle, and it'll take you to that. All right. If you are in the 11 o'clock section, here's a group A. You're in the 11 o'clock section. And then, oh, I need to get group B here. Hold on one second. I need to open up group B. Okay, sorry about that. So here's the groups. If you are in the 11 o'clock class, remember these are your group members. I messaged those of you who were absent on Friday. I messaged you about which group you're going to be with, and I sent you copies of the problem as well. Okay, and if you are in the afternoon group, the B group, these are your groups. If you have questions about your group or whatever, let me know, and I will get back to you. And thanks. I hope you all have a good day. As always, send me questions, send me questions, send me questions. Thanks.